Hello everyone, welcome to Practically. We bring learning alive. As you all know, we have started a series called Comprehensive, right? Comprehensive series that we have started where we are going to cover the complete organic reaction mechanism. Where we have already started and we have taken one session for SN2 reaction mechanism. Okay. Now in this today's session, I'm going to cover SN1 reaction mechanism. Now many of the points of SN1 reaction has already been covered in SN2 only because the effect of solvent and the effect of nucleophile and all that we have already covered. Okay, but there are some other things that we still need to see that we're going to see today in SN1 reaction mechanism. Okay, so on that note, let's begin. So the very first, now here you can see the structure of tertiary butyl chloride. Okay, this is the structure of tertiary butyl chloride, and that is what? That is your OH minus, right? That is your OH minus. This is where its negative charge is. Now, what is happening here? Your negative charge wala hydroxide. I would rather say it has only hydroxide ion. Hydroxide ion is trying to attack the carbon from the front side, but chlorine is not allowing it to attack. Basically, there is a fight. There is a fight between chlorine and hydroxide ion, as you can see here. See, they are fighting. Okay. See, they are basically fighting. Now, fighting means that literally do not take this meaning as fighting. They are fighting because, see, you can see here, what are these? These are your lone pairs. Lone pairs of chlorine as well as lone pairs of oxygen. And lone pairs are means what? Lone pairs are nothing but the electrons. So we know that there is a repulsion between electron and electron. So that repulsion is not allowing oxygen to attack from the front side. Okay, that's the main reason. So what does your oxygen think is that? Oxygen think is that I should attack from the back side. Then it tries to attack from the back side. Okay, or let me take the slide a little bit further, sorry, a little bit backward, then I will tell you. See, firstly, they are quarreling like this, so it's not allowing, so it is attacking from the back side. Now, when it tries to attack from the back side, in earlier case, what was happening is that in earlier case, we had a substrate called methyl chloride. In methyl chloride, it was pretty easy to attack from the back side. Why it was easy? Because instead of this methyl, there was only hydrogen there. Okay, so there was no steric hindrance felt by your oxygen from the back side. So it prefers to attack from the back side, and that is how the inversion happens. We had already seen that. Okay, but what is happening now? In this case, see, front side attack is always prohibited. It was prohibited in SN2 also. It was prohibited in SN1 also. I'm talking about before the bond actually gets broken. Okay, so it tries to attack from the back side. In SN2 it was possible, but in SN1 that is also not possible. Why? In SN1 both the attacks, front side, back side, both the attacks are not possible because from the back side also, you have bulky methyl groups. You have these bulky methyl groups. So your oxygen, when it tries to attack, it finds it very, very much difficult to attack because there is no place. There is a steric hindrance, there is a steric repulsion between these groups and these groups also. Okay, so that's the case. That is why I have shown you the, what I would rather say, fight between these and these groups here also. See, that is always happen. So now what's the option? If front side attack is not possible, if back side attack is also not possible, then what's the option? See, reaction is happening anyways. Reaction is happening anyways, but people knew, or scientists knew, that it is not possible to attack from either side. Then what? There must be a mechanism, or there must be a system where bond is getting broken firstly. See, now you can see here the bond has already started breaking here. Bond has started breaking firstly. Bond breaks. See, chlorine goes. bond just goes and you are left with only tertiary carbocation. You are left with what? You are left with tertiary carbocation. Now, see, in SN1, so what is actually happening is that, as you know, what I had written is that SN1. Okay? What do we mean by that one? One stands for unimolecular, right? When I took SN2, it was bimolecular. When I'm talking about SN1, it's a unimolecular. It's a substitution nucleophilic unimolecular reaction, right? That means rate of reaction here is dependent on concentration of only one species. And that one species is what? That one species is substrate. Because see, there are two steps here. SN2 was a single step process. I would rather say it was a concerted process. Everything was happening simultaneously. Whereas your SN1 is a two-step process. Firstly, there's a breaking of bond, which we just saw, right? The breaking of bond between carbon and chlorine. I would rather say heterolytic stage. A heterolytic stage or heterolysis, where the bond has been broken to generate cation and anion. Anion was Cl minus, cation was your carbocation. Okay, and the second stage now would be attacked by your nucleophile. Second stage would be attacked by your nucleophile, and that is how you want to get the product. So it's a two-step mechanism. Okay, the first step, which was breaking of carbon and chlorine bond, first step, which was breaking of carbon and chlorine bond, is the slow step, which we just saw. That is the slow step. And you have seen what species were involved in the slow step. Do you know how they actually find out the mechanism? How they actually find out? Okay, this is the first order, this is the second order, or these are the species on which reaction is dependent. See, what they do is that they means they were scientists. Okay, so they investigate all the steps. Okay, the step which is more slower, whatever number of species or whatever different types of species which are present in that slower step will decide the fate, or I would say will decide the rate of that reaction. And right now we had just seen in this lower step, which was the heterolysis, only substrate was present. There was not present a nucleophile. Nucleophile wasn't there. Nucleophile hasn't come into the picture just as now. I showed you in the first step because I wanted to show that attack from both the sides is not possible for nucleophile now. That is why what reaction do is that reaction opts for breaking of the carbon-chlorine bond. So as soon as that bond gets broken, then nucleophile would attack. Okay, but as I told you, the breaking of bond between carbon and chlorine is the slowest step in this reaction mechanism. Since it's a slowest reaction, it's a slowest step in the reaction mechanism, the rate will be decided only and only by substrate. Okay. Sure. Moving ahead now. Now, as I told you, this is how your nucleophile, your carbocation actually looks like. But in reality, let me show you the real structure. It actually looks like this. So this is your CH3, CH3, CH3. You have a plus charge here, and this is its empty orbital. What is it? It's your empty orbital. Which empty orbital? Which was remained there after breaking of bond. You remember carbon-chlorine bond was actually formed through this orbital. It was formed through this orbital. When carbon-chlorine departed, chlorine took both these electrons, leaving behind an empty p orbital, which is perpendicular, to this trigonal planar. See, that's how it actually is. This is trigonal planar carbocation. perpendicular to which is empty orbital. Okay. Now this empty orbital is going to decide, or this empty orbital is going to accept the electrons from the nucleophile. Okay. So moving ahead now. See, this is how your carbon actually looks like. This is top view, and one more thing. Instead of hydrogen, there is a carbon there. There is a carbon CH3, then you have a CH3, CH3. Here also CH3, CH3, and C. So you can see a vacant p orbital, or you can say empty p orbital. And whenever your nucleophile comes, whenever it comes, it tries to attack either from top side, or it will try to attack from the back side. Sorry, bottom side. It will try to attack either from the top side, or try to attack from the bottom side. So that is how the real definition of your SN1 reaction is all about. Okay. Sure. Moving ahead now. See, now that you are clear how the carbon actually forms, what are the species reaction is dependent on, where does nucleophile attacks on. Now let's see the stereochemistry. Now see, let me tell you, whenever the carbon forms, or let me take you a little bit backward. See here. Now this is your front side. Let me change the color of it. So this is your front side. Right? That's your front side. And this is what? This is your back side. Now the attack from both the sides is equally probable. Attack from both the sides is equally probable. That is what actually happens. Your nucleophile tries to attack from this side, and nucleophile tries to attack from this side also. So technically 50% attack happens from the front side, and 50% attack happens from the back side. 50% attack happens from the front side, 50% attack happens from the back side. Because there is an equal probability. It's not that I wanted to know, or I wanted to distribute it, but tum aadha lo, tum aadha lo. It's not like that. Because attack from both the sides was equally probable, equally possible, and that is why it attacked from both the sides. So as we all know, if it tries to attack from the front side, then what will happen? There will be a retention of stereochemistry. If it attacks from the back side, we know that we had seen in SN2, whenever it tries to attack, or whenever it attacks from the back side, there is an inversion of stereochemistry. Okay. So in this case, there is a half retention of stereochemistry, because half of the molecules attacks from the front side and half molecule attack from the back side. So there's a half retention and half inversion of configuration. If you ask me, in an overall it is called as racemization. Racemization means what? There is a equal formation of D and L isomer. Okay? So if you have started with the D isomer in alkyl halide, it will end up with 50% D isomer of alcohol and 50% L isomer of. Okay? That is what you have studied at least in a NCERT. Okay, but I'm going to tell you something ahead of that. Okay? So before moving ahead of that, let me show you how this actually happens. Okay? Let's see now. Yeah. Now see, here your nucleophile is attacking from the back side. See, you must be seeing the umbrella. Umbrella is there. Now the inversion will start happening. It will happen through this shape, okay, and then you will see the umbrella completely inverted. See, this is where you started with, this is where you end up with. So there is an inversion of configuration because attack is happening now from the back side. Okay. Now the next step. Here your nucleophile is actually attacking from the front side. So when it tries to attack, or whenever it attacks from the front side or from the side where living group was actually present, then what happens? Then the stereochemistry remains as it was. Stereochemistry remains as it was. Okay? So there is a 50% possibility of this, 50% possibility of the last slide. Okay? That is what you have at least studied in your NCERT. Okay? But there is a more to it. Okay? Let's see this first. Again here, same thing is happening. See, this is where your living group is present. Now this nucleophile is attacking from the back side of your nucleophile. You got the inversion. When it attacks from the front side, it got the retention. Okay, but in reality, what if I tell you that there is a more inversion than a retention? That means initially I told you that there is a 50% retention and 50% inversion. But what if I tell you that percentage of inversion is more than the percentage of retention? I'm not saying rationalization does not happen here. Rationalization does happen. But the percentage of inversion is more than the percentage of retention. Do you know why? Let me tell you. See, suppose this is your substrate. Okay. Now I'm not telling you anything with the primary substrate, secondary substrate, whatever it is, primary, secondary, tertiary. I'm just taking substrate. Okay. Now what happens? The solvent comes here and breaks this bond. This bond is getting broken now. Right? Now, what are you getting? You have got the carbocation here, and this is your living. So this living group doesn't go immediately away. This X minus, which is also called as a living group, doesn't go immediately away from your carbocation. It stays there as intimate ion pair. It stays there as intimate ion pair. But nucleophile has already come into system. Nucleophile has already come into system and nucleophile has already started attacking. So what does nucleophile do? Nucleophile tries to attack from the front side. Oh, sorry, I made a mistake here. Yeah. So your so suppose this is your alkyl halide. Okay, this is your alkyl halide. Okay, now it could be your primary, it could be secondary, whatever it could be. Okay. Now, what is happening here is that the bond between them are getting broken just like this. Okay, and whenever the bond gets broken, what do we have? Is that we have carbocation and we have a living group. Now, what do you think? Does the living group departs immediately after breaking the bond, or does it stays there? The answer is it stays there only, and that is what is called as, just a sec, that is what is called as intimate ion pair. That is what is called as intimate ion pair. That means it stays there for some time. Your living group stays there for some time with your carbocation, and whatever time it stays there, see, your nucleophile has already come into system. Your nucleophile has already come there. So it would start attacking. And as soon as it starts attacking, what happens? It starts attacking from the front side as well as it starts attacking from the back side. But from the front side, what do we have? Front side, we have a little bit restriction. We have a little bit restriction from the living group which hasn't departed yet. But till that time, the attack from the back side already started. Okay. Now get my point again. The bond breaks between your halide and the substrate. As soon as the bond gets broken, you get the carbocation and the living group as an intimate ion. Okay? Now those intimate ion pair will be separated from each other completely when the solvent molecule, enters inside. When the solvent molecule enters inside, then this cation anion would be separated completely because then the solvent would solvent them. Okay, that's how the process is. But before that happened, they would stay as intimate ion. And the attack by nucleophile has already started happening from both the sides, front as well as back. Okay, but from the front side, since the nucleophile or living group is already there, the attack from the front side is still prohibited to some extent. However, the attack from the back side is not at all prohibited. So that is why the attack from back side has already started happening, but the attack from front side has not started happening. Okay, until the solid molecule comes, enters inside this intimate ion pair and breaks them apart completely. Now you would have the carbocation in this stage. Now the attack would start happening from both the sides. And now whatever amount of attack happens thereafter would cause inversion. But did you get my point? Inversion would start, racemization would start happening now. But before that, before the intimate ion pair could break into completely separate ions, before that could happen, the attack was happening more from the back side. And that is why the inversion is more in SN1 reaction also. Okay. So if you are appearing for advanced exam, if the question appears like that, the answer should be more inversion. If the question is for only board exam or only for NCT exam, then the racemization is the answer. Okay. Chalo, I hope this point is clear to you now. I have told you both the aspect, NCT wala aspect as well as advanced wala aspect also. Okay. Sure. Now kinetics. Kinetics, I have already told you. Here the rate of the reaction is dependent on the concentration of only and only one species, and that species is what? That species is your substrate. And that is why it's the first order kinetics. This K is net constant, as we already know. And I have told you the reason also why it is dependent only on substrate. Because why it is dependent only on substrate? Because in the slower state, only substrate was present. There was no nucleophile. Okay? Sure. Now, effect of solvent. What is the effect of solvent in SN1 reaction? See, and I just told you that there is a formation of cation and anion in SN1 reaction. So there is a formation of cation and anion. That means what? Only polar solvent. Polar solvent is useful for SN1 reaction. If you decrease the polarity of solvent, the rate of reaction would also be decreased. Why? The first thing, let's see this. What I have told you here is that effect of solvent in SN1 reaction. So the first point that I have pointed out here is that polar solvent promotes ionization. Why polar solvent promotes ionization? I will tell you that, but let's see this. See, SN1 reaction have faster rate in a strongly polar solvent than in a less polar solvent. Polar solvent, by that I mean polar protic solvent. For example, water, ammonia, acetic acid, all of these are polar protic solvent. Okay, so solvent polarity is measured by dielectric polarization, or you can call it the dielectric constant. We already know that, right? Non-polar solvents have no peak. Polar solvents have higher P, we know that. Now between water and your ethanol, which is more polar, you think? Between water and methanol, or ethanol, you can also call it ethanol, between both of this, water is more polar. So more polar solvent would accelerate the rate of your SN1 reaction. You can see here. See, this is your substrate that we had taken. This is your alcohol. Okay, you got what? OR and HCl. So nucleophilic substitution reaction has happened. The solvent relative reactivity. Firstly, they took only ethanol. The rate of reaction was only 1. Then they do what? Then they change the concentration of a solvent. They took 40% water, 60% ethanol. See, the rate became 100. Then they took 80% water, 20% ethanol. The rate became 14,000. Lastly, they took all the water and no alcohol at all. Then the rate became what? 1 into 10 raised to 5, 1 lakh. So as the polarity of solvent increase, the rate of reaction also increase. Basically, the SN1 reaction would be enhanced or would be accelerated by using a polar solvent. More polar the solvent, faster would be the SN1 reaction. The question is why? The main question arises here, why is like that? Okay, so I am here to tell you why. See, so just now I told you that we had taken what? We had taken, this is your substrate, okay, this is your nucleophile. Now what happened? This bond gets broken just like this, and it gives you this cation, and it gives you what? An living group. Okay. Now what does polar solvent do here? See, your polar solvent comes, for example, your water is there. Your water would be solvating your R plus through oxygen from all the sides. See, just like this. See, your water is solvating your R plus from all the sides, just like this. Now, why it is solvating through oxygen only? Because oxygen is having what? Hydrogen is having delta plus. We all know, right? Yeah. Your hydrogen is having delta plus, delta plus. Oxygen is having delta minus. So each oxygen is having delta minus, just like this, 2 delta minus, 2 delta minus, 2 delta minus, and 2 delta. And what do we have on R? We have carbon. We have a plus charge there, no? So it is obvious that it will be soliding. R plus would get solided by water through oxygen. Your X minus would get solided by water molecule through hydrogen. Why? Because hydrogen is having delta plus on H. See, just like that. Now don't count the number of water molecules, that could be more or less dependent on the charge concentration or your cation or. But the point is, see in chemistry you need to know that whenever there is a charge, whenever there is a charge, plus charge, negative charge, or even a single electron, which is called as free radical, right? There is no charge on that, but it's free radical. Whenever you have such species, it will always be less stable. And the neutral species, whenever we are talking about this stability thing, no, you need to understand that everything in the universe, everything in the universe, if it's a neutral, it is more stable. If it has even any kind of charge, it will be less stable. Okay? Now, but the question here is that then does this system, I mean, why the system is making a charge? Because you saw why it is breaking a bond, because there was no option. Reaction was happening anyways. So if the reaction is happening, that means the bond must be breaking between R and X. Now, if the bond is breaking, you are getting carbon and X minus or leaving group. So charge is inevitable. You can't avoid it. But what can you do is that you can bring the solvent. Now, what does solvent do? Whatever process you have seen just now, this process is called as solvation. All this is called as solvation. Okay. What does solvation do? Solvation decreases the density of a charge. Solvation decreases the density of a charge. Charge could be positive, negative, or free radical, whatever it is. So if the density of the charge is getting decreased, as I told you, then you are going towards a neutral thing. So when you are going towards a neutral thing, system becomes more stable. It is that simple. So that is why solvation always increases the rate of reaction of SN1. Because why? See, the rate of reaction here is dependent on the how fast the bond between R and X will be broken. And the speed with which bond is getting broken will be dependent on the type of a solvent. Because see, R and X, whenever they are breaking the bond, they would think, okay, if I break the bond, I will form a carbon and I will form the X minus. So would I be able to get solvented? Would I be able to get would I be able to get stability? Yes or not? They will think. So if they know that polar solvent is there, which is there to help us, the polar solvent is there, which is there to help us to stabilize. Okay, they know this. Then they will break the bond immediately. If they will break the bond immediately, you will immediately form a carbon and the attack will immediately start happening. And that is how the rate of reaction actually increases. Okay, and that's the reason the polar solvent always increases the rate of SN1 reaction, which is the exact opposite to what we had seen in SN2. Okay. Sure. So, effect of solvent. So, we already had seen what effect of solvent is. Here, I am just going to list some of the polar protic solvent which we had seen in SN2 also. See, DMSO, DMA, acetonitrile, hexamethyl phosphoramide, acetone, all of these are polar aprotic solvent. And what are polar protic solvent? The water is there, polar protic solvent, methanol is there, ethanol is there, ammonia is there, tertiary butanol is there, acetic acid is there. Wherever your hydrogen is attached to either nitrogen or oxygen, in fact, halogen also, but the hydrogen attached to halogen are very less solvent. That is why I would take only nitrogen oxygen. So hydrogen attached to nitrogen oxygen, all those solvents are always polar. Okay, amongst them water is most polar. So that is the order of your polar protic solvent. And this point which I have written here, that you will understand when we will finish all the reaction mechanism. Okay, chalo, moving ahead. So effect of structure. Now effect of structure we had seen in SN2 also, that as the steric index around the carbon increases, the rate of SN2 reaction decreases. Now here in SN1, it is exact opposite to what we had seen in SN1. For example, see, we are starting with, or let me take, yeah, so CH3X, CH3, CH2X, then we, oh sorry, then I have CH3, CH, X secondary alkyl halide, and lastly you have a tertiary alkyl halide. See, so this is your 0 degree. I would rather call it as the prime was the methyl alkyl halide or primary. See, people generally call it as a methyl alkyl halide. Call it as a 0 degree because these are 3 degree, 2 degree, 1 degree. If I write that as 0 degree, it will be better to understand. Secondary and okay. Now, oh, that 3 is looking something odd, no? So I will write it again. Yeah, 3 degree. Now, see in SN2, this reactant was the fastest to react. This was the slowest to react. Why? Because in SN2, the attack from front side was prohibited, but attack from the back side was easily accessible because there was no steric hindrance. Okay? In SN1, there is the formation of a carbocation, and we know the stability of carbocation, right? Tertiary carbocation is most stable. We know that the order of stability of carbocation here goes like this. This is the most stable tertiary carbocation, then secondary carbocation, then primary carbocation, and lastly this. Okay, so any substrate which gives you most stable carbocation, mark my word, any substrate which gives you most stable carbocation would also give you the SN1 reaction fastest. It is that simple. So the rate of SN1 reaction as far as substrate is concerned is directly proportional to the stability of a carbocation. That is why order of reactivity also is in this order. That is the fastest to react by SN1. This is the slowest to react by SN1. Or if you summarize it, any substrate which gives you most stable carbocation would also give you SN1 reaction fastest. It is that simple. Again, sure. Moving ahead. Last point. Leaving group of fugacity order. Now, leaving group of fugacity order, we know that if the leaving group is good, the rate of SN1, SN2 reaction would be faster. Now, effect of leaving group order or fugacity order, it is absolutely same on both SN1 and SN2. Mark my words here. The effect of leaving group or fugacity order is same on both SN1 and SN2, and it is exactly same. Okay, so any leaving group which is faster in SN2 or any leaving group which increases the rate of SN2 reaction would also increase the rate of SN1 reaction also. Okay, and we had already seen about this in SN2 also, that what do we do here is that we put the H plus ion into this, right? We put the H plus ion into this, and what do we get? See, this will give you HCOH. This will give you CH3COH. This will give you PHCOH. This will give you Cl3SO3H. The strongest acid will be this. The weakest base formed by that. And weaker the base, good is the leaving. That means the leaving group ability is directly proportional, is inversely proportional to the basicity, or I would say it is directly proportional to the pKa of conjugate acid. So here the base leaving group, the first one would be this one. Okay. Then the last one would be what? Last one would be this one. Right? Well, we have already seen about it, so I don't need to tell you again and again. Here also, if I talk about this, the best leaving group would be your R minus. The best the worst leaving group would be N minus. So which we had already talked about in SN2. Okay, so that is how we summarize both SN1, SN2. Okay, I hope you find this helpful and useful. So please follow us on YouTube, and you can check the channel practically 11-12. Okay, where we gonna put all this comprehensive series, where you will see the videos of physics also, chemistry also, and biology also, and you can get your as many concepts clear as possible. Thank you.